Hey, hello everyone. Welcome to today's edition of Omniverse Live. Really excited to announce this is brand new, guys. We just released Modulus, so hot off the press. We're talking with several members of the Modulus team to talk about what Modulus is and how to get started with it. So before I get into it, first I want to introduce to you two people of the community team. I have with us Mateus, who's the new technical community manager. And we have Edmar. You guys know him. And I'll hand it over to you, Edmar, for some announcements.
Awesome.
Yeah.
Thank you. Very happy to do today's stream. The extension for Modulus just went live hours ago, as you mentioned a couple minutes ago in the warm-up. So welcome to everybody who's tuning in for that. We're going to do a getting started live stream. So give everyone background to what Modulus is, how it relates to machine learning and physics, and what the Omniverse extension does at this point in time. But first, we have a couple of quick things. Number one are, as we've talked about on every live stream the past couple of weeks, we are right now in the middle of the Machinima contest, Made in Machinima. We started to see some submissions roll in from the community, and oh my gosh, they are awesome. So nice shout out to Benny D, who's actually, I think, done 3 or perhaps 4 submissions as of last night. So you can do as many submissions as you like, and you can only win 1 prize, but you can try multiple times. So that is just do a search for Omniverse Machinima contest. It'll come right up, and you have, I believe, until the end of this month. So there's plenty of time. That's going to be really exciting. You can search for the hashtag Made in Machinima, and you'll see some submissions as they start rolling in. So if you have any questions on that, we have a contest channel on the Omniverse Discord, which is, of course, in discord.gg/NVIDIA Omniverse. So lots of great questions and answers there with our team. But we have, as Wendy said, we have a very special guest, and he could probably talk about a couple things. One, which is an awesome thing. I think a bunch of us have been really excited for this to come into fruition for developers. So let's talk about what is happening tomorrow, Matthias. Something big, right?
Yeah. So let me share my screen here, just to have some reference. So first thing is tomorrow we have our first Omniverse Extensions Jam.
Woo-hoo!
And that's going to be a Discord event. You can just jump on Discord between 3 p.m. and 9 p.m. Pacific time, and we'll help you out with building an extension. You can pair up with someone else and work together, and we'll have NVIDIA developers online to help answer questions. You can RSVP on Discord. The link is in the forum announcement, and also you can jump on Discord and see our list of events. And that way we know that we'll have enough support for everybody that's coming to join us. So that's the first thing that's coming up. That's tomorrow. And next week we're kicking off our developer live stream. So we have these live streams on Wednesdays. And we're going to start up on Tuesdays, same time, 11 a.m. Pacific. We're going to have developers coming on and doing more hands-on live coding and getting into the nitty gritty of these things. So these live streams will still be happening, and we'll do high-level overviews for users and developers, and then we'll dive even deeper in the developer streams on Tuesdays.
That is awesome. So yeah, so those will happen about every other week?
Yes, every other week on Tuesdays.
Very cool. So well, that's going to be really exciting, and I think we've got Damien's commitment, who will pop in for the first one next week. He's so we'll have to alert his fan club. But that's going to be really exciting, because I think the developers have been really wanting to kind of work more directly with our team, and now we're going to be able to do that on a weekly or semi-weekly basis. And of course, we have great resources for developers right now and not only on the forums but also on the Discord. We have a category for developers, for people developing extensions and microservices, channel for Warp and physics and stuff. So head on over to the Discord server if you want to chat with users or devs there, but definitely tune into the live stream. Super exciting. Well, thank you, Matthias. Thank you for popping in and sharing that great news. And tomorrow night should be a lot of fun. So I'm looking forward to it.
Yep. Thanks for having me.
Yep. Awesome.
So now it is very exciting. I think we said I feel like developers have been waiting in the wings for us to be ready to be able to support everything they want to do with open arms, and we're at that point now. I think last year we celebrated a lot of artistic endeavors in the community, and now we also want to support developers fully. So a lot of really cool, exciting stuff happening. So a jam is a great way to kick things off. So speaking of developers, so this is a super exciting live stream. We have a few people here, Ram, Boomy, Nick, Bob Miller may even pop in at some point. We'll see. But let's kick it off by actually just saying hello to anyone who has not joined this live stream before. This is the NVIDIA Omniverse live stream. So Omniverse is NVIDIA's open platform for real-time simulation and collaboration. And on this live stream, we try to cover all the different apps and tools and workflows and highlight partners and users doing cool stuff. As I mentioned earlier, the extension from Modulus was just released last night, so anyone can grab it. We're going to walk you through that the second part of this. But I think the first part of the show, we're going to kind of talk about what Modulus is. And to help us do that, we have two special guests, Ram and Boomy. So welcome to the live stream. Let's start with Ram. Ram, do you want to give a quick introduction on yourself, your background, and what you do here in NVIDIA, and then Boomy, and then we'll dive into what Modulus is?
Sure. I'm Ram Cherukuri. I'm the product manager for Modulus. Been at NVIDIA for about 2 years now, so still new, learning a lot of new things. For example, this is my first Discord live stream, so
Nice.
super happy to be here. Yeah, lots of positive energy, so really excited. Yeah, as Idmar, you were mentioning, we're happy to introduce what Modulus is, how we see this technology helping developers, especially engineers. And yeah, we'll talk about that for the rest of the show, but maybe I'll hand it off to Boomy to introduce herself.
Awesome.
Thank you. Hey everyone, I'm Boomy Gaddi. I'm the product marketing manager for Modulus at NVIDIA for a little over 6 months, but I worked in the simulation industry for about 10 years in the past, and happy to be here. First Discord live as well, and very, very exciting opportunity. Thank you for having us.
Awesome. And Nick, let's actually, you might as well introduce yourself now so people aren't wondering the whole time who you are.
So I'm not just the silent partner waiting in the wings. My name is Leaf. I've been with NVIDIA for almost 4 years now. I'm developer technology engineer, which means I'm a software engineer in sort of a customer-facing role typically. And then my niche is what's called HPC visualization, high-performance computing visualization, essentially taking high-performance simulation, turning it into something you can actually render and look at, which is kind of a nice fit for Modulus, because Modulus is simulation, certainly high performance, and getting that data into Omniverse has been very fun to.
That's awesome. So Nick, on the second part of the show, will walk us through actually grabbing the extension and showing us what the workflow is like. So thank you, Nick. All right. So what is Modulus, and who should be most interested in it? What does it kind of allow people to do?
Yeah, Edmar, I can take that. In fact, we maybe want to switch it up a little, right? So instead of making it, theoretical and kind of leaving the the community members to imagine what it looks like, Nick, how about we show what it looks like and then talk about the technology that kind of drives it?
Yes.
Yeah, okay.
Yes. And yes.
Okay. Let's jump right in, and warning, law of demos applies. So things may go wrong, but let's see how this works. Okay.
Nothing's ever gone wrong on this live stream before, by the way.
Never.
No, I'm happy to be the first.
I'm totally
Okay.
lying. Everything goes wrong here.
So here I've started up Create, and what I want to show is just a little bit of what Modulus and the Omniverse integration with Modulus. So first up, I want to go into the extensions window and search for Modulus. Here I have the core extension. One thing to point out is I already have this down. I did that ahead of time. The core extension is a little bit hefty. It's about 1.8 gigabytes. So it takes a little while to download depending on your extension, depending on your connection. Unfortunately, there isn't a progress bar just yet. So if you're downloading it and it seems to be taking a while, just give it some time. So I have the core extension installed, enabled, and now I'm going to go to this FPGA Modulus scenario. This is a predefined scenario we have set up for looking at this airflow through for an I'm enabling that. That might take a little bit to enable because it's setting up a bunch of stuff under the hood. With that set up, you can see something clicked over here, and it's loading up our scene. So we have sort of just an empty scene here. The interesting stuff happens when we go to the lower right and we look at this Modulus. So probably select the property window by default. The Modulus window is where we want to be. So the first thing I'll do is click this isosurface button. And while that's thinking, what we're getting from Modulus is output data. So the data we're mostly interacting with, Modulus is simulating airflow past. The data we're using is the velocity magnet, so the airspeed at a given point defined on a volumetric grid. By putting an isosurface at a fairly low speed, we can see where the air is slowing down, which would be boundary, and then, of course, as it's hitting the cooling fins that you can see here. So because this is Modulus, and this is we're computing this by running inference through Modulus, we can adjust the physical property. So we can increase the height of the heat. And then if I switch my view a little bit, we can increase the length of the. So that shows us what the data looks like. This doesn't really show us what the airflow is. So I'll turn on another visual feature, which is streamline. The streamlines are computed by advecting particles through the airflow. So it's almost like if you had smoke particles, you could track them as they're flowing past this. So this shows us that the airflow is pretty straight, but you can see like a couple of places where the airflow gets disrupted by these sink fins. If I play, we have this animated texture set up for these that show the airspeed. So one interesting difference, most of these are flown past pretty quickly, but you can see that particularly right here, and let me turn off the isosurface so to make that visible. So you can see that in the middle here, we're getting some streamlines that are hitting fins going around. So this gives us a little bit of an idea of how the airflow might react to them. And then as these different properties, like the height and length of those, you might get slightly different airflow. We have some sliders here. These sliders are kind of automatically populated, linked to things that are either part of the pipeline, the visualization pipeline. So if I change, say, the streamline step, that doesn't run inference, that's using the same data, but it's rerunning the underlying visualization pipeline that's computing the streamline. Things like the heatsink height and length, that'll affect the actual module. One last feature that we have predefined here is we can turn on slices. And so this will visualize airspeed along one particular axis. So we can see that, towards the upper side, we're maybe getting some lower air coming in contact with the simulation boundary. And then towards the middle here, we're getting pretty good airflow through that heat. So one thing to point out, as I said, this is all very new, very bleeding edge. This is kind of our first approach at it. So, the UI is maybe a little bit rough looking, still kind of early stages, but we really wanted to get this into people, get them playing with it and see what people do with it, and hopefully give us some inspiration for what you guys and how we can make this better.
Awesome. And so probably the best place for people to submit feedback is on the forums, the official forums we've got. Also, if you notice any bugs, that's the best place to post bugs, because that's integrated with our bug tracking system internally, and so we can track it. And of course, we do have a Discord channel we opened up called Physics-ML, I think. So you can post anything you like there and give us feedback. Yeah, and I think it'd be great to know what people's kind of use would be like, what their cases are, so we can kind of dive into that and help prioritize our next step. So, Nick, you mentioned this is the very beginning. So, so there's plans to expand this extension and add more functionality to it.
Yes, absolutely. So in the future, we definitely want to improve UI a bit. Right now, creating these scenarios involves having that core extension and then making your own extension. Luckily, I heard there's an extension jam tomorrow, so that could be very helpful. But the more streamlined we can make that process, and the easier it is to experiment, the more cool stuff. So that's something we just want to streamline the whole process and really put the tools and give them really nice UI tools with.
Awesome. And on that note, definitely I'm watching the Twitch and YouTube and Discord channels, so feel free to post your questions for the team here, and we'll try to answer during the live stream. And while we wait for those questions to come in, Ram or Bhumi, do you want to add anything to what Nick has said on what Modulus is?
Absolutely. So now that we've seen what the extension enables, let me try to go into the underlying technology. Unfortunately, I can't show things as cool as Nick because I'll have to dive into slideware a little bit. So let me just share my screen, and Edmar, if you can confirm, you guys can
Confirmed.
Confirmed.
Perfect. Okay. So Bhumi and I will just walk you through the underlying technology that makes what Nick just showed possible. And I think I'll reiterate what Nick just mentioned. This is our first step to bringing in Modulus into the Omniverse world. And as we go in the coming months and years, I think there's a lot more possibilities we're excited about. But coming back to Modulus, what is it? We've kind of touched on it a little bit, but let me expand on that. It's a platform for doing physics ML. So physics and machine learning coming together to make certain things possible. So and essentially those certain things are doing simulations faster and faster and accurately. I think that combination is really hard to bring together, and that's what we are trying to do. And in order to talk about that, maybe I'll quickly go over where AI and in engineering and scientific simulations, where do we see that path going and our vision for that, and then put Modulus in the context of that. I think that's the best way to understand where we are approaching Modulus as a platform, and talk about functionalities. Specifically, I want to call out digital twins, because Omniverse is as you guys have been probably experiencing all the different ways you can, but from an engineering and product design standpoint, using it for digital twins and using it for engineering problems is kind of my interest in it. So I want to talk a little bit about that, and ultimately we want to leave it with resources. So if you're intrigued by the things that we shared today, hopefully you can kind of learn more, and definitely, as Edmar pointed out, reach out to us. We like to hear more of the great things people are doing, and if we can improve the platform, we want to learn from the community. Okay, so with that, I want to just set the context about AI-powered computational domains. Nick, maybe you want to mute yourself. I think the key typing. Sorry about that. Yeah, cool. All right. So, of course, NVIDIA is an AI company. So, in the last decade, GPUs have, really ushered in this AI decade, right? Where we have seen computer vision, natural language processing. Now it has deep learning and AI have become part of our lives. And we want to see the same in the engineering domain, in the HPC space, as Nick was pointing out. And we think it is possible. And we want to be an enabler in that journey, if you will. So that's where Modulus sort of was conceived. We started off with the engineering domain, the computational engineering. So when you think of problems like computational fluid dynamics, it could be thermal and heat transfer, acoustics, etc. That's where we started applying AI principles and trying to see how we can augment traditional simulation techniques. But just to also give you where this path leads to, it's not specific to just computational engineering. The same principles can be applied to leverage AI in the domain of earth sciences, life sciences, computational physics, and we are seeing some early customers do some pretty cool things. And we talk about this at all of our events like GTCs. And again, in the resources section, that's where I point you to kind of hopefully inspire you to look at this and think of creative ways of applying the same technology and also challenging us, right, in doing more. Okay, with that, maybe this is a good context to set where I just said that, hey, AI has been really taken off in the last decade. So the obvious question is, hey, if it has really taken off, why can't we just apply the same principles to these different domains that I'm talking about? There are a few challenges. People have tried, and we've kind of realized that there are some fundamental things that we need to acknowledge the differences. So to do that, I'm thinking of a simple engineering problem, right? If you think of a clinical technician that is trying to simulate or look at the blood flow through an aneurysm, right, in such a setting. And I'm taking this just to maybe kind of paint a dramatic picture as well. That's even that simple simulation is pretty large for an AI problem. The input image here could be millions of data points, and that's still not as easy to do or quick to do today. So the reason that's important is we don't have to purely rely on AI for that, because we have decades and centuries old information that's available to us in the form of, hey, there are governing laws that dictate how blood flows through our veins, right? So we can use that information to augment these simulations, right, to make them work together. So how do we do that? So that's one unique thing about these kinds of problems. And then the second one is when you just take those AI architectures and apply to these kinds of problems, typically you run into problems like convergence. Hey, the model doesn't really converge. Therefore, you actually require to think about these architectures a bit more, given these new class of problems. And then one well-known bias, it's known as spectral bias, is our computer vision techniques. They try to, they're generally biased towards low-frequency solutions, whereas these engineering problems and problems in these life sciences, they can have partially higher order partial differential equations, nonlinearities. So that bias really doesn't capture the overall solution space. So those are just two examples to kind of illustrate the point that we need different approaches to kind of solve problems that are governed by physics equations and to make them physically consistent. In addition to that, there's another way to think about it is AI itself brings about new capabilities, and we can start addressing different categories of use cases. Initially, I talked about, hey, how can we augment traditional simulation techniques? But you can also think about data-driven problems. So when you have data and you're trying to infer the characteristics of the system, that's classic deep learning, right? And AI, that's what it's really good at. So those kinds of problems can now be solved using AI and physics ML. And then if you go back, what I just mentioned, that doing things accurately and fast is a pretty hard combination to achieve. And that's where I think AI trained models, they make it possible, and that opens us up to new possibilities like building real-time digital twins, and usually we associate the word digital twins for things that have already been built. But if you think about even the product design phase, you can use that to explore your design space for design optimization, those kinds of problems. And I've just given you a couple of examples here for in each category, because these are possible in Modulus today. So I want to generate more confidence that, hey, it's already been done, and then of course we can explore it for a wider variety of use cases and richer use cases, more complex use cases. So in a nutshell, Modulus is a physics ML platform that takes both data and the governing equations and kind of uses them both to come up with a AI model that you can use to infer the simulation behavior over and over again. So if you look back at what Nick just showed, such a model can be used to infer the simulation behavior, and more importantly, when you parameterize that model, when you train it with parameters built into the model, you can in near real time get the simulation behavior by changing those parameters, as we saw with the sliders in Nick's example. So those are some powerful capabilities that enable things like digital twins, in product design, etc. So we have those use cases as proof points. I encourage you to check out the Modulus product page. That's a good go-to place if you're new to this one. Definitely try to look at the resources, try to understand the technology, and of course reach out to us. And then we have, of course, partnerships in the industry and academic world to push the boundaries. As Nick mentioned, this is bleeding edge, so we are definitely we will not say that this is a proven solution by any means. We are pushing the boundaries of science, AI, and application of AI in science. So we welcome you to join us in that journey. Okay, so maybe this is something that we can skip. Essentially, in Modulus, there are a few bits that I want to highlight. I keep mentioning the word platform. The reason for that is we think of Modulus as this toolbox that provides different approaches. And one thing we have learned in kind of doing so ourselves is that no one approach fits all kinds of problems, right? So that's usually very hard. That's rarely the case. So depending on the class of problems, you might have to take up different approaches to that. And we want Modulus to be that platform that provides these different approaches, so you can, as an end user, choose the right approach and build on top of it. To give you an example of that is within Modulus today, we provide purely physics-driven models, which means that you don't require any data. You just need the governing equations, and we'll just go running with those physics equations to build the AI models. Now that succeeds for a certain class of problems, but that's not sufficient for maybe another class of problems. Now that's where we can go to the other extreme, which is we can be purely data driven, right? There are certain class of problems where you don't need equations, or you don't understand the system well enough to have those equations. So you just have data. You say, hey, I have gobs and gobs of data. How can I use the data to just train an AI model? And then there's everything in between, right? And then you can do smart ways of combining data plus physics. So we are working on enabling all of those different approaches, and the end user gets to pick what's the right approach for their particular problem. And now focusing on the user, that's where we want their time and energy to go in, which is bring their domain expertise and try to map their problem and see how they can leverage AI for their problems, rather than focusing on the lower level details, right? It's like if there are folks in the audience that have tried to use AI, let's say 5 years ago, using TensorFlow, it was painful. You needed to be a computer scientist to be able to say, oh, how do I set up this network using C++? Today it's all higher level abstraction, right? We want to be able to use Python and have that convenience. So you guys do the science, that what you build, what you're interested in, and leave the computer science out, and hopefully we take care of it for you. So that's kind of our hope in building this platform. So again, going back to an earlier point that I made about novel architectures that are needed. So here is an example of that. So these are not your common convolutional neural networks that you would heard of, that you hear of in the computer vision and natural language processing. These are different approaches, again, because newer approaches are needed. Fourier neural networks, Fourier feature networks, these use Fourier transforms to avoid the spectral bias that I kind of mentioned in the earlier slide. So we provide these curated architectures, and we do so in the context of reference examples, because, as I said, not one architecture can solve different kinds of problems. So at least by sharing it in the context of a sample reference example, we say, hey, these kinds of problems work very well with these architectures. So, and then that could be your starting point, and then from there off you go. You can, bring your own expertise, and then, you can even go and build new network architectures that become your IP, and you're building on top of it. And more recently, I want to call out a lot of work goes on within NVIDIA in the AI space. So NVIDIA research team has been working on this new class of networks called neural operators. You'll be hearing them more in the future as well, especially as we work more and more on climate science type problems. These are physics guided neural network architectures that seem to do really well for some of these large scale problems like climate science. So this is all in the documentation, so I'll probably skip this slide. And again, I'll point to our documentation because, again, if it's new to you, that's where we try to do a good job of providing a primer of what these techniques are. Of course, these are not, papers are the best place if you really want to have a full, thorough knowledge of what these techniques are, but that's not needed for everybody. So in our documentation is a good primer for you to learn about these. Now, more importantly, let's talk about applications of Modulus. So because Modulus is a general platform, it actually can be used for a wide variety of problems. In fact, your domain becomes an input, right? What I mean by that is, earlier I said, hey, we take both data and the governing equations. So none of those talk about, hey, the governing equations. So none of those talk about, hey, it has to be domain specific, right? So your data can be from any domain, and your equations could be from any domain as well. So if you go from CFD to solid mechanics to acoustics, what is changing is your type of equations are different, but at the end of the day, these are partial differential equations. So it's the same for us. So in that way, Modulus is general enough that you can apply it to different class of problems. And we also demonstrate this through our examples. So you have examples for computational fluid dynamics, solid mechanics, acoustics, and electromagnetics, vibrations, turbulence. So it is possible. So that's kind of my point here is do check out those examples to kind of see how we have applied the same core principles for different class of problems. And then I think that should get you started on thinking about how your problem can, or rather how Modulus can apply and benefit in your use case or problem that you're trying to solve. Going back to this categorization, I want to talk a little bit about each of these examples as well to give you, again, a sense of how it's being used by industry today. The first one is the Siemens Gamesa. So Siemens Gamesa is a company that is a big player in the wind energy market. So of course they're trying to build wind farms that are very optimal and have the maximum energy output, right? So that's their end goal. But in doing so, it takes a lot of engineering, as you might imagine, right? They're trying to optimize how to position the different each of the turbine so they maximize the energy output, and to do so they have what are known as engineering wake models. So these are models that are reduced order models that have been developed by the industry, and the main thing there is they actually take in simulation data as input so that they can synthesize their data into a smaller approximate form so that they can use they can use it as part of optimization. Now, so the key takeaway there is they require simulation data. They require good simulation data to have better wake models, right? Now, that's always a problem. Just to give you a sense of why that's a problem, for a single turbine, if you were to do a high fidelity simulation, it takes about 40 days on a 100 CPU cluster, right? Just to give you some context of the complexity and computational cost of it. So how does Modulus help there, right? We've been talking about augmenting traditional simulations. This was pretty cool, and we have the demo there, and in fact we can post in the Twitch channel the paper that we emulated as well. We essentially train an AI model that can take a low resolution simulation and super resolve it to give you the same high fidelity simulation output that you would get from the higher fidelity simulations. So in fact, you are getting, if you look at it from a time perspective, you're getting a 4000x speed up by doing so, because you're doing a low resolution simulation, which is faster, but then you're getting the high resolution output. So this is essentially done by using generative adversarial networks. So that's pretty common in the computer vision space. So applying that to the engineering world, if you will. So two takeaways there would be yes, this is being applied to large scale real world problems. And second thing is there is a benefit here, which is it's actually enabling previously things that we said, hey, that is impractical. Now that's making that possible, right? Again, I will not go through the video. There's a link to the YouTube video, which is pretty cool in my opinion. So please go check it out. Nick, in fact, worked on the visualization part. So please do check that out. The next one is, in fact, on the other side, which is on the product design side. We talked about the ability to parameterize. So if I were to simplify this, here, what this company was trying to do is they were designing this air knife. You see at the bottom here, changing the animation, right? So the curvature of that blade was a parameter. And then they trained an AI model with that parameter specified. So once you had the trained model, you can vary or go through variation of that parameter, just like Nick showed. You could have a slider bar and then see how the simulation changes and find that optimal point where you're getting the right simulation behavior. That gives you the right product design configuration, if you will, right? So that's one good example of how this parameterization can help in the product design space. Again, going back to this one, another example I want to talk about, this is almost NVIDIA internal. We meaning, I don't know if folks have been following NVIDIA, we try to eat our own dog food so that we have better products coming out. This is a good example of that, right? So when Modulus was being developed, they said, hey, okay, we design our heat sinks, right? And kind of Nick showed a simplified example of that. So we said, okay, let's design better heat sinks using Modulus. You say you can do you can do parameterized models and you can come up with better design configurations. Why don't we just do that? And in fact, that was the exercise that we did with this example with our DGX heatsink. And of course, I can't spill all the beans, but we have had some good outcomes from there that have led into product design changes. And that was very satisfying to see that the technology works. And we kind of, that was our validation point, saying this can be helpful to the outside world as well. And lastly, I want to talk about digital twins, because you'll be hearing more of this in the context of Omniverse, right? This is the virtual world where we want to be able to do a lot of cool things. So digital twins have lots of, real world value proposition. One is, you can, if you're using it earlier, as I've been saying, in the product design phase, you can do product design optimization, design exploration. But if you're also thinking about post deployment, people are using one of the classic use cases for digital twins is, how do I make sure that my assets in the field are operational and are efficient in their operation, right? So you can do experiments in the design in the digital world to determine and kind of explore those scenarios and take those insights and then use them in your real world, so that your real world system is kind of at its peak performance, if you will. That's usually the outcome. So an example of this is our work with Siemens Energy. So they operate about 600 or so power plants all over the world. Their goal is to minimize downtime and have a better assessment of when they need to shut down the plant. Right today, they do it, every 6 months is a good time, or something, some cadence like that. And that's not driven by traditional. They're not doing simulations to determine it. They know that by past experience, that's a good rule of thumb, right? So that means they're of course factoring in redundancy and things like that. So they could be more efficient in that process. And the way they wanted to do that is. Previously, if they were to rely on traditional simulations, of course, it takes really long time, and that's not a reasonable way to base their decisions on. So they wanted something accurate and fast. So that's where again Modulus came into the picture. We trained an AI model that can simulate flow through their heat recovery steam generator, and as you change the turbine operating point, how does that impact the simulation? How does that accelerate the corrosion of the pipes? If they were to get that simulation feedback pretty quickly, then they can figure out when they should plan for downtime. So please check out that demo as well. That's available on YouTube. Another flavor of that example, we have another agency, NETL. They're doing pretty cool work in again power plant boilers, how to run them efficiently so that they can minimize the the exhaust that come out of the power plant by making it more efficient, right? So they're doing digital twin. They're trying to build digital twins to do that, and Modulus is the brains, and then Omniverse is the platform where they experiment with the different operational conditions, if you will. So I've kind of walked through all the examples except for this last one, and I want to talk a little bit about inverse problems. So this is a simple example of a 2D flow over a heatsink. Here, essentially, we want to use data, simulation or experimental data that you have, and you want to infer, parameters. In this case, it's the viscosity of the fluid flowing over the heatsink, right? So these kinds of problems are previously not possible with traditional ISV, traditional solvers, but this is kind of bread and butter for AI and machine learning techniques. So you're able to do that using Modulus. And similar, and I have another example similar to the digital twin one here. This is just to drive home the point that, again, this is an academic research work that happened about application of digital twins for aircraft servicing, and just to drive home the point that there's a lot more research that needs to happen in this space to fully benefit from this technology going forward. Okay, so these couple of slides just summarize what Nick just showed. As I said, as kind of Nick highlighted, this is our first release, so we are being cautious. We call it a preview release, so bear with us. We hope to make this a lot more feature-rich and functional for you guys. But the first release, we focused on two key things. One is most HPC simulation problems, visualization is a core piece of that, right? So previously, we relied on the end user taking the outputs produced by Modulus, which are usually just NumPy arrays, so it's just data. And then we kind of said, hey, go visualize it wherever you want, right? Wherever you're comfortable. But we have this great platform called Omniverse, and that is built to do visualization in a super rich way. So we said, hey, we want to enable that pipeline so that the data that is produced by Modulus, you're able to visualize it and gain insights from it. So that's point number one. And the second one was to do the real-time interactive exploration, like Nick just showed, right? You're being able to change the parameters and see, hey, what does that do to my system? And that's where we want to further build on to make it more intuitive, be able to do different kinds of visualization and things like that. So we hope to build on that in the future releases. But for this release, that was our focus. That was our MVP, to really get that in the first release. And you kind of saw that. So this slide is optional. Now, sorry, I'm segueing into now the big picture a little bit. So, we talked about different kinds of engineering problems that we have worked with customers, we have through examples, but we think that this technology can apply across different domains, and to kind of prove that point, I'm trying to show where we are applying this to, right? At all of our GTC events, you're going to hear us talk about climate research and how we want to help accelerate that. And we are building a digital twin of the Earth, which is going to be a massive undertaking. But underlying that, Modulus is trying to play its part by providing the brains, which is the AI model that is going to, do some of the simulation. So NVIDIA Modulus is being used to build those AI models to predict extreme weather phenomena. And recently we announced a new model called ForecastNet that can be trained on Modulus. So it predicts extreme weather phenomena, at par and better than state-of-the-art numerical models. So again, no means we are a proven technology yet, but it can do a lot today. So that should not prevent you from looking at Modulus. In fact, you should try to push the boundaries and let us know if it fails, because that's where we tend to learn, right? That's where new features and enhancements come into. So please check out this if you're interested in how NVIDIA, what work we are doing on the weather side. And I'll leave you at that. Again, there of course there's a video on YouTube. Check it out for the simulation aspect of it, if you will. And then maybe Bhumi, you want to talk through all the resources, great resources that you've been collating for end users?
Sure. Thank you. We'll be posting the links to all the demos and the channels shortly. I think Edmar, I'll collaborate with you to do so. And then the Modulus resources links will be also posted here. So first of all, please go to the Modulus product page on developer.nvidia.com. We have a lot of featured contents, which includes the GDC sessions that have been done on Modulus. There are also links to documentation and how you can get access to Modulus, where you can download it from, and stuff like that. So please go there and check those resources out.
That's awesome. I am blown by the power of using this to tackle it seems like some really, really difficult, challenging problems in the world. Using an immense amount of data, but so it looks to save resources or time or money. Seems like just a very powerful tool set. In the chat, we've seen a bunch of people actually just spit out all these different use cases they can see for this. So a lot of excitement. I'm getting some private messages on Discord now about it too. So definitely a lot of excitement. So that's great. If anyone has any specific questions, now would be that time to ask, so we can kind of challenge our guests with those questions. So where do you see this moving forward? So obviously GTC, we're going to be showing off a bunch of stuff. And I think there was also a good reference from last GTC. If people want to watch the previous session, you did cover some of this, right?
Yes. The demos that we are showing in different use case slides that Ram was showing, they're all actually from previous GTC and the GTC before.
Great. So I think if anyone doesn't know, you can basically search through previous GTC presentations very easily through the session catalog. And some sessions may require just a registration, that's all. But they should all be there. But Ram, you actually gave a presentation at the most recent GTC, right?
Yes. So again, the theme with all of these is to share proof points and how it was done, so that it can inspire more folks to think about their problems. And hopefully benefit from what is available in the platform today. So yeah, at last GDC we presented the Siemens Energy use case, which I just mentioned briefly, kind of how we went about that problem, and then and then there was another presentation just talking about how we are thinking about the climate science type of problems and how we are applying Modulus there. So those are pretty good talks if you're interested in those domains.
Excellent. You're already inspiring one of our power users. Papa Chuck is already saying that he needs to get 2 PhDs so he can take full advantage of this technology.
Yes. Yay.
I support you, Papa Chuck.
Yeah, I loved how you said that you guys can do the science, we do the computations. That's really exciting to me. My son is getting his PhD in genetic engineering, and he's actually had to minor in data science because because there isn't really anything available for him to do automatically or with AI. So this is going to be awesome.
No, yeah. So I think thanks for sharing that, Wendy, because my wife is in the the biology world, so she keeps complaining that hey, we need more technology in that space, and of course
Yes.
things are changing, but could not come fast enough, right? They can probably benefit for a lot of this, and someone in the audience probably has a brilliant idea that they can build on, and hopefully we can help them along the way, right? That's the hope.
This is going to be awesome.
Looks like folks are actually posting new ideas in the chat.
Yeah, I see that. We do have one question, lots of interesting ideas. And one question, does Modulus support dynamic ISO surfaces? It almost looked real time in the FPGA demo.
We can't hear your audio.
Yeah, the audio did cut out. So the question, can you hear me okay?
Yes.
Okay, so the question is, does Modulus support dynamic ISO surfaces? It almost looked real time in the FPGA demo. It is real time, it's Omniverse.
Okay, cool. I don't know if my audio is working better now, but let me see. I think what we can do now in these last minutes, unless anyone here that's on the panel would like to stress anything that maybe went over really quickly or something we missed. Otherwise, we could take these next few minutes to join the community over on our Discord server to ask any questions in real time. But I'll go around. Does anyone have anything else to add before we close out the stream session?
Is my mic working?
It
Yes.
is. I'm sorry.
Perfect.
That was
No
my
worries.
fault.
Okay.
I had muted you because your keyboard was going, and I forgot to unmute you. So I
Okay.
apologize.
Yeah. No worries. No worries. I had totally forgotten about the angry typing thing. On the ISO surface thing, yes, the ISO surfaces are near real time. So we're taking that velocity data directly from Modulus, and so that's the output of Modulus. That's inferred simulation data, and computing the ISO surface behind the scenes. Right in Omniverse. We're using VTK-M under the hood, if you're familiar with it, so the data can be mostly resident on the GPU while we're using that visualization pipeline. And then just one other thing I was thinking of while Bram was talking and going through all this, for me, coming from the Viz side, one of the most exciting things about this OV Modulus integration is reducing and shortening the loop, that iteration time from thinking of a new design idea to running the simulation to visualizing, by being able to get Modulus and get the Modulus inference into Omniverse and being able to explore that design space interactively. You might explore ideas you had never wanted to take the time, that seemed a little bit more off the wall than you could otherwise, because who's going to spend how many days of simulation time on a whim, right? But if you can just do it in a couple seconds, yeah, you're exploring things you might not otherwise.
Not have said that better myself, Nick. Yeah, absolutely.
So we have another question, actually. So for those who don't know, NVIDIA has a Deep Learning Institute, or DLI, where we offer courses on different topics. One of the most popular ones we have recently is a course going over USD. And a lot of really great feedback from people who have taken that course, and you leave that really have a great understanding of the file format that really is kind of helps supporting the existence of Omniverse in a lot of ways by allowing all these different apps and tools to communicate with each other easily. So the question is there DLI content planned for Modulus, or is there currently any?
I can take that one, Edmar. Yes, we are working on the DLI content and a full-fledged course for a couple of hours long, and that should be posted up soon. So we'll make sure to post the link to the course in the Physics ML channel on Discord once it's live.
Awesome.
That is great. And let me ask you, actually, this is a question just as a side note, but why is it better that we have the channel called Physics ML versus Modulus?
Right. So as I said, Modulus is the platform, but the technology in general is kind of Physics ML is the word that's getting used a lot for that. So I think we'd be interested in understanding from a technology perspective what people are doing. They don't have to necessarily use Modulus, but it'd be good to get that conversation going. Within the community, sharing ideas, which is exactly what I think people do on channels like these. So that was inspiration.
Perfect.
It may be
Okay.
Modulus today, tomorrow it could be something else, right? So
That makes total sense. So what we'll do on that Discord channel, Physics ML, we will start posting some pinned documents there. So if you're just getting started, if you go to the top of the channel, you'll see this description about the channel, and then we'll add a lot of stuff there. And that should be your one-stop shopping for getting started. And of course, the forums. So do the forums have a specific area also to discuss physics machine learning?
Right. There is a special NVIDIA Modulus form, or we should say like physics informed neural network channel that's there on NVIDIA forums, which essentially is Modulus. But again, we don't want to call it Modulus, we want to call it by technology, so people can post like beyond Modulus any questions they may have in that arena,
Awesome. Perfect. Okay. So anyone have any last comments, parting words?
Yeah, no, again, thanks for all the questions that we've been getting, feedback. We look to the community for feedback that gives us, the right, it's a compass, right, to tell we are going in the right way. So please share your experiences with us, and we hope to improve the, product and the functionalities.
Thank you. And just a big congratulations to the team at NVIDIA for getting the extension published last night, and obviously all the work that goes into that is a lot. So thank you for coming on so soon after that to share everything with the community. And if you all have a few minutes now, we could jump on Discord really quick. We'll go to the community voice chat channel. Maybe we can share Wendy's VO performance from Pekka's short film to anyone. So that'll be a little nugget for people to come over to the voice chat channel. But thank you all so much, though. Thank you, Wendy, for, of course, handling all the complicated stuff in the background and making these live streams work so well. So thank you, everybody.
Absolutely.
Thank you.
Thanks, everyone. We'll see you soon.
Thank you so
See you
much.
next week.
Thank you, guys.